In last video, we have talked about the Fourier series for continuous time periodic signal, but in many problems, we will encounter a aperiodic and finite duration signal. This time, we will use a new tool, so-called Fourier transform, also invented by Fourier, this great mathematician from France. In Fourier series, we will use two equations. The first equation can transform a time domain signal, so-called S of t, into a frequency domain signal, so-called S of j omega, by this integration. In the second equation, we can transform a frequency domain signal, so-called S of j omega, to a time domain signal S of t. You can treat the second equation as the recovery for the x of t from S of j omega. You should notice both of the integration integrate with a very large range, at least in the formula, from minus infinity to positive infinity. But in the first expression, we will integrate with t. In the second, we will integrate with omega. Additional feature is in the second expression, we will use this 1 over 2 pi as a part of this equation. Okay, let's see some example. You can see in example 3 and example 4, the signal are very similar, but the difference is also very explicit. That is, the independent variable or so-called field is different. In example 3, the independent variable is t. In example 4, the field is omega. Because the second equation related to example 4 is relatively complex, we will only conduct the second example, example 4. Now let's use the integration 1 over 2 pi. Integrate from minus infinity, but it is a finite duration signal. We can only integrate from minus omega 1 to omega 1. For Sj omega, we use this amplitude that's a constant relative to omega, a, and basis function e power j omega t. Integrate with omega. Place a out of the integration, a over 2 pi, from minus omega 1, e power j omega t, d omega. This integration, we have encountered a similar form in Fourier series problem. Let's review it. Here, let's copy it to compile. If you see these two integration, you will see the biggest difference is independent variable, or what we will integrate with. Now we should conduct d omega, but last time we conduct with dt. But the principle is almost same. We can treat omega as t and treat t as omega. That is ej t omega dt. Integrate from minus t1 to t1. And by this equivalent form, you will get this result from last time exercise 1 over j omega e j t1 omega minus E J minus T1 omega. Use Euler formula sine omega T1. Okay, because we have changed the variable, we should change back to its original form. So 2 over T sine, here omega is T, T1 is omega 1. This final result, let's move it. Eliminate 2. You can see A sine omega 1 t over pi t. Some experiences can be summarized from this long-run deduction. In this integration, whatever we integrate with omega or integrate with t, this notion treats this complex variable function as a real variable function is same. What do I mean? That is, we can directly conduct this integration. Let's try it. Because omega is what we will integrate with, so we should divide it by jt and place the original function ej omega t. We will plug in the lower limit and the upper limit omega equal omega 1, omega equal minus omega 1, and plug in 2. If you try it by yourself, you will get the exactly same result as this result. So in conclusion, from this example 4, you can learn 2 things. The first one is how do we use the inverse Fourier transform formula. And the second thing is, for this integration, whatever we conduct with omega or conduct with t, that is the exactly same with real variable exponential. For Fourier transform, these 2 formulas are very important.